First, I want to thank the conveners for giving me the chance to present our work we compiled during the last years. And this talk is about nitrous oxide. So it's over there. So in this session, there's also CO2, methane, and also one talk of nitrous oxide. And compared to CO2 and methane, nitrous oxide can't actually compete because CO2 is a big player in radiative forcing. And for methane, there's hypothesis that there's glacier destabilization and some weird things in permafrost. But usually nitrous oxide is kind of boring. But actually I like it because for CO2, at least I have the impression, oh, we already know it, but that's not true. But for nitrous oxide, we really can a lot because little attention there was little effort on that. And to learn more about the processes, so the overwhelming part of nitrous oxide released from the terrestrial biosphere, from soils, and a smaller fraction is released from marine ecosystems, mainly oxygen minimum zones. And the only tool we really have to distinguish the two sources are the isotopes. So in the bottoms you see 15N of nitrous oxide, on the y-axis you see 18O, and you see that the marine samples taken by many cruise ships where they cluster on the right side, so it's a heavy source, and the terrestrial source is light. And you see it's a wide range, so it's complicated, but the mean of these two sources is different, and there's approximately 10 to 20 per mil difference between the two sources. And Todd Sowers was actually the first to manage to measure it 14 years ago, and he essentially got it. The main features he got already. So, and he found out that minimal change in the ratio of marine and terrestrial in production. So it means he got a flat line in the isotopes essentially, and the consequence is that if you have changes in the atmosphere, so the only possibility is that the two sources change in parallel. And after a while, so 11 years, so there was a new measurement device ready in Oregon, and Adrian Schild led a paper which focused on the last termination, and essentially they came to the same conclusion, so parallel changes of both sources, but they also found intervals during young-wood rise and these phases where the kind of decoupling, whereas the marine source goes down and terrestrial source goes up. But essentially, they go in parallel. And a few years later, in Bern, we measured and measured and measured and collected, and also set up a model led by Fortunat and Renato and many others. And so we now have a record covering not only the termination, but also the LGM and the Holocene. So we have a complete record of that. But there's more. And so the last years we measured the whole glacial cycle. So we filled the glacial gap and have a well-resolved Eemian record. And there's some gaps in between where we actually lack of ice because we can't measure every ice core. So in principle, during the glacial, only high accumulation sites are usable. So Yellowstone and Wace, and all the other cores have problems with in situ production. So it relies on one or two cores. And this is a nitrous oxide cycle. Or the coupling between carbon and, so you see the tree, which represents the carbon cycle, and then you have a big wheel representing the nitrogen cycle, and I don't have time to explain everything, but you see that there's there's N2O production during the recycling process and during nitrification and denitrification. And so this is our source to the atmosphere. And in principle, so the main emitters are low latitudes, so the tropics, where there's lots of rainfall, and these sites, so Pantanal and all these low latitudes, are the dominant source. And as I said, there's also production in the ocean, oxygen minimum zones, which is seen here, and the main process is denitrification here. And the main feature of our records is, as I said, so the difference between marine and terrestrial is around 15, but the signal we see in our ice cores is relatively tiny. It's 2 per mil. And what we did in this paper, which has to be resubmitted, and so we used a mass balance approach. So we used the nitrogen isotopic composition of N2O and deconvolved the two sources, and the result you see here. So we have total emissions from the ice cores, and with the help of the isotopes, we split it in the marine and land emissions. And you see here that during the Heinrich, we have a drop in marine emissions, but overall, these two emissions go mostly in parallel. And this is a zoom into the last glacial period, so where we have the prominent Danske-Röschke events, which have nitrous oxide amplitudes which are comparable to glacial interglacials. And as expected, so there is only little signal in these DO events, especially in DO 21, where we do have the largest signal in the whole record. And so the message is clear. So the isotopes say, so the sources must go in parallel, which is actually really puzzling, because the common knowledge is that the ocean production should release from these denitrification zones, and then the biosphere kicks in. So we should see a complex evolution, but we don't. And the second feature we see for the first time actually is our long-term trends. So in first order everything's flat, but we see a long-term trend towards the LGM. So this scale ends at 35. So there's a long-term trend, and we again see the decoupling because 18O is flat. So this is the decoupling because in a simple view, 15N and 18O should always be correlated if we argue with two end members. And the funny thing is, so we see this upward trend, and we see the downward trend during the termination and early Holocene. And so we can't really, because 18O is flat, so we can't really use this deconvolution or mass balance approach to explain it. But it's a robust feature what we see. So we see it again during the Eemian, or started the Eemian, and we see upward trend. So we see actually a bowl shape during the last interglacial. And we also have, so again, here's the last, the LGM and Holocene, and here's plotted the last interglacial, and we also have data from MIS 11, where we measured, and I can only look at the interglacials because the glacial sections of the EDC core, so there's in situ production, and we only have data really from the interglacials, which are enclosed in clean ice. And so the observation is really that we always see this bowl shape, and But of course, for a Holocene, there's no glaciation, and perhaps won't for a long time. Thanks. And one explanation, though there's others, because you can do the game also with the marine part. So one explanation is related to that paper. So in that paper, this group, they collected sedimentary 15N, so a global study. They looked at the change, the trend, throughout the Holocene, or starting with the termination. And they saw that 15N in the terrestrial biosphere has a long-term trend. And their interpretation actually is that it's related to net carbon sequestration. So when the vegetation is growing or ecosystem expand, so new carbon is actually sequestered, and the biosphere needs nitrogen to do that. And this is actually supported by other evidences from carbon isotopes and also by carbonyl sulfide. And the simple idea of that is the following. It's just a very simple approach. And so we have nitrogen fixation, so it's a flow-through model in essence. So we have nitrogen fixation, which has a 15N of 0, and then we have the recycling loop, the biosphere and the soil nitrogen, and then we have loss, which has a fractionation involved. And in steady state, input is output, and we have a different signature over there. And I assume that during the last glacier, so during the LGM, we are in a steady state situation. And when the deglaciation starts, so the tree is growing, so they need more nitrogen. So the pool increases, and so it's actually diluted with new nitrogen, which has 0. So the whole pool goes down, and so it could explain this downward trend just from that shift in the pool. And this brings me to the end. So we have the first dual isotope evolution during the last glacial cycle. This is new. And these things you already saw in Todd Sauer's statement. So because these data are still correct, so I can only repeat it, but we now have it in better precision. So there's only minor changes in the isotopic composition. So the sources, so we have to find processes really which allow a simultaneous increase from the ocean and the marine, from the terrestrial. And this is what I had in the last section of the talk. So to explain these long-term trends by suggesting that carbon and nitrogen cycle is coupled, and when there's net uptake of carbon, we get a shift in the mean nitrogen signature. Okay. Thank you.
So I'm not sure what happens with the nitrogen at the bottom of the ocean, but wouldn't you expect a signal during the ventilation events when the ocean isn't stratified anymore during the terminations?
Yeah, we would. So Andreas Schmitt, for example, I think 10 years ago, put forward the model. So when during the deglaciation or during DO events, during the statal, there's N2O release. But we can't see that. So, or there's a magic process in the terrestrial biosphere with just the same flux, so it cancels out. Okay. So we need some magic.
Yeah, thank you.
I haven't kept up with this. I was just wondering, it used to be that there was large error bars on the source isotopic composition, because another possibility is that actually the source isotopic composition is just much more similar than is thought. Is that still possible?
Yeah, it's not really error bars, it's just that the source signature, so the mean or the model, is not really known. So the people tried hard to get it, but the sampling is insufficient.
So it could just be that actually they're not very different, and that's why you don't see.
It could be. That's
changes.
one possibility. Yeah.
We're going to look into the processes driving the atmospheric CO2 increase during Heinrich 1. So Heinrich 1 occurred at the beginning of the last deglaciation and was marked by a shutdown of North Atlantic deep water formation, which maintained Greenland and the North Atlantic into a glacial state, while Antarctic temperature and atmospheric CO2 increased. So it is a very crucial period to understand, so Heinrich 1, because this is the time period where you have a main phase of deglaciation at high southern latitude and also a main phase of atmospheric CO2 increase. And now, thanks to high-resolution Antarctic ice core record, we can see a bit more of the structure of the atmospheric CO2 increase, which occur in like 2 phases here, which we'll look into more detail later, and also was coincident with a decrease in the carbon isotopic composition of atmospheric CO2, which can hopefully help to constrain the mechanism at play here. So, so here we'll look into this question: what led to the atmospheric CO2 increase during Heinrich 1 and the delta C13 CO2 decrease? So to do that, we'll perform transient simulation of Heinrich 1 with a carbon isotope-enabled Earth system model. So we will run it transiently from the last glacial maximum up until across H1, so during the cold phase, and we will stop right before the transition into the boiling air and it will be run with prognostic atmospheric CO2 and delta C13 CO2, meaning that those variables are computed by the model. It's not a forcing. And our initial state is a last glacial maximum, which was constrained by its carbon isotopic distribution. So we spend a lot of time on it. And it's characterized by here relatively weak, well, I say weak 12 sphere drop, and shallow, about 2,500 meters, North Atlantic deep water, or glacial North Atlantic intermediate water, as you wish. Very weak Antarctic bottom water, and a North Pacific intermediate water, which is, I don't know, I would call relatively weak, about 6 sphere drop and about 1,000 meters. So what we do is we start from this state, and we will add a bit of fresh water in the North Atlantic to shut down North Atlantic deep water formation. And when we do that, actually not much happens, really. We have no significant change in atmospheric CO2, no change in delta C13 CO2. Our global SST is actually so very minor change, and a very small decrease in southern hemispheric sea ice. So we just stay in a glacial state. So this is a bit what happened to the carbon cycle. So if we look at the average GIC anomaly over the Atlantic and the Pacific, here we're decreasing significantly the ventilation in the Atlantic, and therefore increasing our carbon content in most of the Atlantic, particularly on the north. On the other side, in these models, through oceanic and atmospheric teleconnection, we have an increase in the North Pacific intermediate water, and therefore we're ventilating the North Pacific. So basically, we have a transfer of carbon from the Pacific into the Atlantic with no net change in atmospheric CO2. So obviously, this is a problem. But in this state, if you remember, our glacial state has very weak Antarctic bottom water, so very stratified Southern Ocean. And we know from Proxy records that potentially there was an increase in Southern Ocean ventilation. So now what we're going to do is we're going to force a strengthening of this Antarctic bottom water, basically through a lower buoyancy forcing in the Southern Ocean. We're going to trigger an increase in Antarctic bottom water. So this is what we do here. We have basically a 2-step increase in Antarctic bottom water, very significant increase. And as a result, we now have an atmospheric CO2 increase. It looks small, but it's actually 18 ppm, which is very significant. But you can see the slope is just a very gradual increase. So it's a multi-centennial scale increase in atmospheric CO2, which is also matched by a decrease in delta C13 of CO2. So this time, if we go back to our DIC anomaly, we still have a lot of carbon in the North Atlantic, but this time we're ventilating the Southern Ocean, ventilating a bit of the deep Atlantic, but really ventilating the deep Pacific. So this time we have a transfer of carbon from the deep ocean into the surface to the surface ocean and outgassing through the Southern Ocean. And in terms of delta C13 CO2, just very briefly, so again what we're doing is that we are ventilating the bottom ocean, which is DIC rich and has a very low delta C13 signature, so you're bringing DIC rich, low delta C13 signature to the surface, which can lead to an atmospheric delta C13 CO2 decrease. And a very interesting part of this mechanism is that as you increase your ventilation in the Southern Ocean, so increase your Antarctic bottom water, you're also increasing the meridional heat transport to the high southern latitude, so a bit like the same mechanisms that you see in the North Atlantic, if you wish, which lead to a very significant warming in the Southern Ocean, in Antarctica, and a very large decrease in sea ice. So we have a 40% sea ice decrease. So the point is, not only do you outgas CO2, but also you start to deglaciate the high southern latitude, and you actually go into a deglaciation. But now you see we have a kind of a problem basically on the shape of the change, and also we can wonder how can we get stronger Antarctic bottom water. And we know that a strong control on Antarctic bottom water are the southern hemispheric westerlies. And Li and Chang in 2010, for example, put out a mechanism whereby when you cool the North Atlantic, you have a southward shift of the intertropical convergence zone. So this is a robust feature. When you shift southward, you ITCZs, and you can have a weakening of the Hadley cell, the southern hemispheric Hadley cell, which can strengthen the southern hemispheric westerly and eventually shift them poleward. So now what we're going to do is we're going to strengthen the westerlies, not outrageously, we're strengthening them by about 20%, so 20% wind stress increase. And now here you see we have a stronger increase in Antarctic bottom water, much sharper transition, and interestingly, our atmospheric CO2 first increased more in its amplitude, but also the shape is different. We have very rapid transition. So for example, here we have about 8 to 10 ppm in just about 50 years. So it is a very sharp, very rapid transition, also matched here in its isotopic composition. So what we're doing is that, as in the buoyancy forcing case, we are ventilating the Southern Ocean, ventilating the bottom of the ocean, so bringing this DIC-rich water to the surface, but we know that this is a slow process, a multi-centennial scale process. But on top of it, we're ventilating the intermediate water. And the intermediate water are much more accessible. You can ventilate them on a much shorter time scale. And very interestingly, we know that the Antarctic intermediate water has very low alkalinity. And you know that the atmospheric CO2 content is not only dependent on the DIC changes, but also on alkalinity. So you need a high DIC over alkalinity ratio to have a high atmospheric CO2 increase. And of course, as we increase the westerlies, we also increase the air-sea gas exchange, which also help to change this content. And here I'm just showing you how we are actually bringing this deep carbon to the surface. So this is a control case with very stratified ocean, large sea ice, and not much happening. And here where we increase the westerlies, we shift our sea ice edge towards Antarctica, and we have a strong CO2 outgassing in the Southern Ocean. Okay, but now we know that the Southern Ocean is a fairly difficult region. It's dynamically complex with lots of mesoscale activity. So many AD activity is going to change the dynamics and the transport of heat, nutrients, carbon, etc. So to make sure that the mechanism we're putting here is robust, we're going to perform an additional simulation. And this time we're going to very high resolution ocean sea ice carbon cycle model. So this is eddy permitting, so we're quarter degree by quarter degree. So this is a very expensive simulation, million CPU hours. We could only run it for 50 years, so it's just very short. But what we did is that we shift the westerly over the Southern Ocean by 4 degrees south, and we increase them by 15%. So this is actually what happened in the last 20 years and what is projected to happen by the end of the century. So this is not an unrealistic scenario. And it is done under constant pre-industrial condition. And you can see that this is a control run here with fairly strong Antarctic bottom water. But when we shift the westerly poleward and increase them, we have a 10th fair drop increase in Antarctic bottom water, which leads to a decrease in our oceanic carbon content by about 60 gigaton in 50 years. So this is not a coupled model, but let's say if you just transit 60 gigaton very crudely into PCO2, that would be 20 ppm. Of course, you know that's not going to happen because the terrestrial biosphere and other processes will come into play. But this is just to show you that very rapidly you can have a significant change in ocean carbon content by changing the westerlies. So now we can just have a look at what happens to the deep ocean. So I will show you an animation of DIC at 4,400 meters. And you can see that the DIC anomaly are actually propagating from the Southern Ocean into the Northwest Pacific and a bit of the Atlantic. So this is really at the bottom over the 50 years, and we're reaching about here not quite 20 north after 50 years. So this is this slow process of ventilating the bottom. Maybe I can show it another time. Here, go. Colors are not perfect, but anyway, so we're also ventilating the intermediate water in that case, and so this decrease in carbon at the bottom is matched by a CO2 flux out of the Southern Ocean. So you can see here, so those are anomalies. And it's still running. Maybe we can see another time. Here we go. So it's very short, but basically you see that this is possible. Basically, when you shift the westerlies and strengthen them, you can ventilate your deep ocean and have a CO2 outgassing of the Southern Ocean. So just to conclude, basically, so the point of it is not that I want to explain everything with the westerlies, but I think that increase in Southern Ocean ventilation is a key to go to deglaciate, basically. It will lead to an atmospheric CO2 increase, and it will lead to climate change that can then lead to a deglaciation. If you don't have this change in ventilation in the Southern Ocean, it will be very hard to get out of a glacial state. So basically here we have a shutdown on North Atlantic deep water formation, which will cool the North Atlantic further, shift the ITCZ to the south, weaken the Southern Hemispheric Hadley cell, potentially strengthening and shifting poleward the Southern Hemispheric westerlies. So in that case, you start to increase the ventilation of the Antarctic intermediate water, which is a very fast process with a very high DIC over alkalinity ratio, leading to an atmospheric CO2 increase. So this is the fast part of it. On a much slower part, we know that we have an Antarctic bottom water increase, so increase of the deep ocean, which slowly lead to this CO2 outgassing. But very importantly, we know that the increase in Antarctic bottom water will lead to warmer conditions at high southern latitudes, so an increase in Southern Ocean SST, increase in Antarctic temperature, increase in sea ice, we can then feed back onto the atmospheric CO2 and also lead to a decrease in delta C13 CO2. Thank you.
When you change the westerlies, have you looked what happened to the physical pump and the biological pump? So have you changes in marine export production?
Yeah, we do.
What's more important, physical or biology?
I think it's physical. Well, I mean, the biological part is very complex, obviously. And when you look at the marine export records, you will see that they don't change at the same time in the latitude. So if you go to the last glacial maximum, you have a high productivity north of the polar front. And this changed very rapidly. So if you look at the Martinez-Garcia record, the change in productivity is very early. It's like 20K to 18K, and then you're back to very low productivity. But on the other case, when you start to go poleward, you see an increase in productivity during H1, which can be also fairly late, if you wish, for the Anderson record, which started to increase about 16K, right? And I think that the hypothesis that was put forward is that there was an increase in upwelling. And I think it is consistent because in our record, obviously, if you increase the Southern Ocean ventilation, we will increase the productivity.
Great. Okay, thanks very much for coming, everyone. Thank you for giving me the opportunity to speak. Thank you all for nestling into the dungeon down here. So for the last 30 years, we've thought that CO2 storage and release in the deep Southern Ocean, as Laurie just wonderfully introduced for us, plays a key role in these interglacial cycles in CO2. And we have great ideas now, and indeed model simulations, of several of the processes that could play a role in changing CO2. So changes in circulation, changes in sea ice, changes in the efficiency of the biological pump. However, records of deep CO2 itself have been more elusive. So this is something that Jim and you and myself have both been working on quite extensively. But often when we look at deep CO2 records from boron isotopes or boron calcium in the Atlantic or the Pacific, we're confounded by changes in water mass or the influence of carbonate compensation. So in search of this deep Southern Ocean CO2, we went further and deeper into the Southern Ocean itself, and are going to present today a new record of boron isotopes from deep sea corals from the Drake Passage. Now, I'd be happy to talk about the systematics of this in more detail with anyone who's interested, but for the purposes of today's talk, the key thing you just need to know is that boron isotopes reflect the pH of the water that carbonate grows in, and pH is, of course, closely coupled to CO2 chemistry. So more CO2, lower pH. So our sites come from two main groups from the Drake Passage. One grouping further south of the polar front and in slightly deeper waters, recording the kind of carbon-rich lower cell of the ocean. And a second group further north of the polar front and somewhat shallower, recording the upper cell waters. Now, these corals have been dated really with exquisite precision by Andrea Burke and Tianyu Chen with uranium to thorium decay. And then we've measured replicate boron isotope samples from lots of individual pieces from these corals at our new labs at the University of St. Andrews. Okay, so here are the data. So essentially what you can see here is the last deglaciation here. This is the last 45,000 years with a compilation of different CO2 records here. And then here are our data, replicate samples from the same corals shown in open symbols with their mean as the filled symbol. So what you can see is that our deep southern sites record more CO2-rich, lower pH waters at the LGM, and that this rises over the deglaciation. And this is also reflected in the upper cell corals, which have relatively higher pH, reflecting the transfer of carbon from the upper ocean and the atmosphere into the abyss. So now, looking into this in more detail, we can see this tight coupling between deep southern pH and atmospheric CO2, even on this millennial timescale. So when CO2 is relatively high, deep southern ocean pH is relatively high. As CO2 then falls, pH then falls, reflecting enhanced CO2 storage in the deep southern ocean. There's a range of processes that may contribute to this. Laurie's talked about some of them really nicely. Here are records of a few of them. You can store more carbon in the deep southern ocean via changes in circulation, via changes in the efficiency of the biological pump, and perhaps also via changes in sea ice. And it's kind of interesting, all of these have some correspondence with this record of deep CO2 in the Southern Ocean. Though it's interesting that there's maybe a particularly nice correspondence with the waste divide sea salt sodium record. And perhaps sea ice is quite an effective mechanism through its coupled influence both on circulation and also on CO2 outgassing. One other really interesting aspect of these data is you can see during kind of peak glacial conditions in MIS2, we see these kind of further pH minima associated with these sea ice maxima. And while there's some kind of inflection in CO2, this is kind of muted. So despite the fact that it seems that kind of circulation, the biological pump, sea ice, and indeed kind of Southern Ocean CO2 storage itself are all acting to try and get CO2 out of the atmosphere, atmospheric CO2 doesn't go much lower. And this kind of ties in perhaps kind of interestingly to a really kind of fascinating recent paper by Eric Galbraith and Sarah Eggleston, who suggested that perhaps this lower limit on CO2 may come about due to CO2 limitation on primary productivity. So now going into the upper cell, we start out with relatively high pH waters reflecting the transfer of CO2 out of the upper ocean and the atmosphere. And then during these intervals of millennial scale and indeed centennial scale CO2 rise, we see pronounced minima in our upper cell coral sites. And this reflects, we think, the transfer of carbon-rich waters out of the deep Southern Ocean and into the upper reaches of the ocean, exactly as Laurie just showed with that nice simulation. So looking into this in more detail, you can see this kind of fascinating feature that these minima in pH, suggesting the arrival of the most CO2-rich waters into the upper reaches of the Southern Ocean, are synchronous with these amazing jumps in the waste divide CO2 record. And since Sean Marcotte published this in 2014, I mean, this has just been an amazing stimulus to the community to make us think about the carbon cycle. I mean, and it's been suggested that perhaps, you know, these are too fast for the Southern Ocean. You know, do we have to invoke you know, inputs of carbon from terrestrial reservoirs or from methane hydrates? And I guess I'd say that the short answer to that is that's not required. The Southern Ocean seems to be able to release CO2 on both millennial and even centennial timescales. So what drives this? And I want to finish off the talk by kind of speculating on some mechanisms that may tie these things together. And this is motivated largely by a few key observations. So the first is that these pH minima are synchronous within age uncertainty. And remember that the dating uncertainty on these is kind of plus or minus 50 years. These are synchronous with these rapid jumps in CO2 and these rapid jumps in Greenland isotopes, often thought to reflect onset of NADW formation. However, it's unlikely that the pH minima reflects the input of NADW itself, which is typically a high pH water mass. The rapid recoveries in pH after these events, that may be NADW arriving in the Southern Ocean, but the pH minima themselves they really shouldn't be. Further to that, actually, so this is observation 2, you see this pattern of kind of ever more rapidly decreasing pH in these upper cell Southern Ocean sites prior to this abrupt jump here. So it seems that these processes kind of get going and then reach some kind of peak prior to these rapid jumps here, which might suggest something in the south. But there's also kind of notably, you know, there's not some kind of massive state change in our Antarctic records. This instead has led us to an idea where maybe there's some kind of threshold response lurking in the abyss. And so the nub of this is really informed by a series of lovely recent papers that tie our latest understanding of residual overturning circulation in the Southern Ocean to glacial interglacial climate change. And so, for instance, Raf Ferrari and Andrea Burke propose that in a cooling climate, expansion of sea ice in the Southern Ocean will shoal the boundary between the lower and the upper overturning cells, allowing CO2 and salt to become isolated in the abyss. Then, as we go into a northern hemisphere stadial, the southern hemisphere warms, as proposed by Thomas Stocker here via the bipolar seesaw, and this will allow sea ice to retreat back in the Southern Ocean, as we see in the sea salt sodium records. Now, this will deepen this cell boundary, and this means that this water here, so this is water that was previously in the lower cell, it's rich in CO2, rich in salt, now it comes up north of the sea ice edge and is advected, it gains buoyancy, it's advected northward. So it rejoins the upper cell of the ocean, and this CO2 can be reconnected with the atmosphere. Then, as you further warm the south and further deepen this boundary, sorry if you can't see this at the back, that further deepening of the boundary will put the boundary between the lower and upper cells into this zone of kind of vigorous mixing over rough bottom topography in the deep ocean. And this could really increase the flux of CO2 and salt out of the deep ocean into the upper cell, and may contribute to this rapid rise in CO2, this minima in pH, and may even help the re-establishment of NADW. So, to think about this more generally, this may indeed tie to models of how we might get these amazing series of rapid climate changes during middling glacial climate states in MIS3. The key thing being that expansion and retraction of sea ice via the bipolar seesaw, so inherently tied to what's going on in the north as well, may allow more or less salt and CO2 storage in the abyss. And this is kind of analogous to Wally Broca's original salt oscillator idea for rapid climate change in an off state of NADW, right? You can build up salt in the Atlantic and then reach some abrupt threshold here. We're proposing that may happen by mining salt out of the abyss. And then when NADW is back on, sea ice expands again in the Southern Ocean, salt and CO2 become restored in the abyss. And so well, I guess I'm almost out of time, but this could kind of explain the occurrence of rapid climate change during these kind of middling climate states where sea ice can move quite sensitively and drive the cell boundary over this zone of rough mixing, as opposed to perhaps in MIS2 where the rapid expansion and the kind of far northerly expansion of sea ice may mean that you never really get into this rough mixing zone. And so we tentatively referring to this as the rough salty bottom water oscillator. Okay, so to finish up, really the key point, and it's fun to kind of think about this idea at the end, but the key point that I want you to take away from this is that we have now this really nice direct proxy record of CO2 storage and release in the Southern Ocean. This has been talked about for the last 30 years, and there's different processes that could contribute to it, but we do indeed see it. We can see that deep CO2 storage in the Southern Ocean during cold periods with low atmospheric CO2, and its release as atmospheric CO2 rises. And this may take place on both millennial and indeed centennial timescales. Thank you very much.
Have you thought of bringing in the radiocarbon story into your narrative? And if so, what would you say about that?
So yes, absolutely. Somewhere in there was that was the initial schematic. I still think that one actually might be clearer than my laborious Illustrator effort last night. Oh, okay, it's going to be too embarrassing if I flick much further back. Somewhere in there is the radiocarbon story. Yes, it's super linked in and really interesting. There's a lovely correspondence on the millennial timescale with Julia Gottschalk and Luke Skinner's nice new record over MIS3. And then over the deglaciation, there's this really interesting correspondence with enhanced ventilation in the deep, but then actually in these, so we have the radiocarbon data from these very same corals that was published by Andrea and Laura in 2012 and Tian Yu as well in 2015. And the radiocarbon in the corals shows these kind of two competing influences, we think, of, on the one hand, better ventilation, wanting to make it young, but on the other hand, the transfer of old carbon into that water. So actually, the signals over some of these transitions in the coral radiocarbon are relatively muted compared to the radiocarbon signatures in the deep ocean that you see in the sediment cores.
Very nice talk, James. I have two inquiries. The first one is, the change in boron isotopes is fairly large, up to 3 per mil. If you transfer this change to deep water carbonate, what would that be? The second question is, you are trying to link the deep ocean carbon storage to PCO2. I think this is quite remote. what about the deep ocean carbon reorganization? Okay, if you shift carbon from one location to another, it doesn't always mean the change will be associated with PCO2 changes in the atmosphere. Thank you.
Thank you, Jim, and great questions. So, so on the first, I point out that actually the calibrations of deep-sea coral boron isotopes to pH are more sensitive than that of benthic forams. So those large kind of 3 per mil changes aren't as big as the equivalent would be if you saw it in a planktonic or a benthic foram. We may see a kind of dynamic range here of about half a pH unit at max, but probably more like kind of 0.3, 0.4. Nonetheless, quite large, because I think we are in a kind of sensitive location. Secondly, I absolutely agree that that a range of different processes and different places can play an important role in the atmospheric CO2 question. I mean, I guess, yes, absolutely, I agree. However, I guess I might draw on Laurie's excellent talk just before mine, which showed that these particular sites in the Southern Ocean, when you see changes in their carbonate chemistry, you do see very pronounced changes in the carbon chemistry of the atmosphere. And she showed that nicely mechanistically with the model, and I think here we have the data counterpart to that.
It's a slight shift in focus because it's mainly dealing with the interaction of different Earth system components, also on different time scales. Sorry? It's better? Is it working? So it's dealing with the interaction of different Earth system components and also dealing on these interactions on slightly different time scales. To dive into the topic, did I? Is this back and forth? Which one? I thought this is back and forth.
Oh, maybe just use this then.
Which is back and forth here? This one. Okay. So at the beginning, some classic records. So basically, you know all these records. It's on the lower panel we see CO2 record of over the last 800,000 years, on top delta D as a surrogate for temperature. And what we see here is an extraordinary correlation between CO2 and temperature. And this is a pretty robust relationship during the last 800,000 years. And so basically you can explain about 70 to 80% of the variance in the CO2 signal just by linear regression modeling. Nevertheless, as always, so exceptions prove the rule, and what we see here is a classic record from Barnola. And there are times, for instance, here during the last glacial cycle, so here the glacial inception basically, and then here the transition from MRS 5 to MRS 4, where for some reason CO2 is held up at a relatively high level, while temperatures really tend to drop down in a very pronounced way. And that is a sort of decoupling which has been already mentioned in that paper. And please have note that the time axis is now from the left to the right. So in order to get a feeling how big the magnitude and the Wolf timescales are, we plotted different key records. So basically green EDC temperature, so green orange SST reconstruction on top of obligity. And what we see here is that during a time of decreased obligity, so during the MIS 5.4 boundary, we see a disconnect of CO2 and temperature in the order of about 18 ppm after 9 kiloyears. And basically this also holds true for earlier parts, and if we now plot again these key records individually plus Northgrid, then here the temperature records on a global scale in CO2, so CO2 stays up, and we combine that now with key sea level records, then we see clearly that during these events there are severe drops in sea level and that accompany this decoupling. So we can basically extend that decoupling of CO2 and temperature to sea level. Just to mention, we just not just investigated these two particular events, but also found that this relationship is relatively stable during the last 800,000 years. And this is an interesting feature because during the last years there was a huge momentum in these sort of solid Earth climate component interactions. And there are basically two branches. So one interaction is via ice sheet changes. So it's basically here the classical Heuwers-Langmuir paper. And they basically found that if you have deglaciation, you get a unloading of ice sheet over the continents, and then they detect a higher number of eruption frequencies, and they relate that to an increased enhanced volcanic degassing. So the other branch basically has a look on mid-ocean ridge systems and the associated melting regions. And of course, if you then, let's say, you drop sea level because you have an ice sheet built up, then of course you get a decompression that will also lead to enhanced melting in these zones. So as I said, there have been very nice, very thorough studies about that. So basically about the component associated with the pressure load on the continental plate, but also on the subsystem of the mid-ocean ridges. But somehow this is quite an overlooked part within the marine system, which is basically the hotspot volcanism. And that is even more surprising because the plumes really have a deep source. And the CO2 concentration within their source material is supposed to be much higher than the source material at mid-ocean ridges. So it's really, the hypothesis to test is really, is it possible to held up atmospheric CO2 in the records as we have seen it by that sort of sea level interaction. And in order to address that, it's not straightforward, and we basically established a new novel global plume melting model approach on a global scale, and basically it's based on a three-dimensional mental convection model code, and the mental flow is basically given by a viscous creep of an incompressible fluid, and we can individually resolve 43 different hotspots as shown here on the map. And probably the best known and studied example also in terms of constraints is the so-called Hawaiian Plume. And with that approach, we are able to have reasonable spatial characteristics in the development and in the equilibrium structure of such a plume shape. What is shown here is a temperature surface at 1,400 degrees Celsius. And what you see basically here is that there's a huge lateral expansion of that plume system that is far beyond in its horizontal extension, beyond the plume root. And this is basically a consequence of the direction of the plate, so that exits a viscous coupling on this system. So now, if the mantle is upwelling within the root, then you get a decompression, and basically once you cross a solidus, melting starts, which is basically here the black region. And on top of that, because CO2 is a highly incompatible component within the matrix, that takes preferentially part in the melt phase right at the bottom of this melting zone. And also this melting zone is obviously, in terms of horizontal extent, is much beyond the plume steam. And now we can, of course, envisage if we have a drop in sea level, then of course the upwelling mantle will experience additional decompression, which then in turn gives you additional melting, and by extension also increased fluxes of CO2 and the melt extraction. So, but of course, before we quantify that, we have to do homework, and the global integration across all 43 hotspot systems show that we are able to reproduce cornerstone numbers that are related to about 2 cubic kilometers per year of total melt within all these melt chambers, and that gives you an associated CO2 flux of 0.127 gigatons CO2 per year. And Of course, if we want to set that in the broader context of the total marine volcanism contribution, we also have to address then, of course, mid-ocean ridges. That's what we always also did, but I don't go into the details. What we find is that the baseline flux is, of course, because of the much greater spatial extension, is much bigger than from the oceanic hotspots. But, of course, due to the different source signature or source concentration of CO2 within the melt, the concentration here, the flux in CO2 is bigger for the oceanic hotspot volcanoes. So if we apply a sea level change of 60 meters within 15 kiloyears, we basically find these flux numbers. Again, this here is slightly bigger than the value here. And due to the uncertainties in the different sea level scenarios, we performed many different scenarios of sea level drops in the order of 60 to 100 meters within 5 to 15 kiloyears. And by that, we find that the average CO2 mobilization within these scenarios is about 42 gigatons CO2 per 10 meters for hotspots and 31 gigatons CO2 for mid-ocean ridges. So, which suggests that in that game, even the so far not considered hotspot volcanism is a dominant key player. And the job is still not done because obviously the CO2 that is additionally injected into the atmosphere is then, of course, damped within the atmosphere-ocean system. And what we see here are different scenarios. So for simplicity, submarine and full subaerial sources and a bicycle, so a global carbon cycle box model, and an atmosphere-ocean sediment configuration that takes into account carbonate condensation feedback. And what we model here is changes in the atmospheric CO2 concentrations in the order of about 5 to 9 ppm. For the submarine sources, the spikes are damped by about 10 to 20%. And in the end, we end up with an airborne fraction of about 6%. So this is rather low. To set that into context with other models, model intercomparison has been performed. So this is basically based on straightforward results of Yoast, and then an impulse response function has been derived by a study from Lord and applied in order to see how for a reference injection of CO2 within 1 year the system would behave on the long-term time scales. And what we see here in magenta and in blue is basically the bicycle performance, and you see that we are at the lower end of this model spread. It's 2 sigma here. So basically, there's a fairly good basis to argue that the contributions of that impact could be up to 250% of what we see here within this left-hand side panel. So in that sense, we think that the associated mechanism and the interaction might be potentially very powerful. And to just briefly summarize and wrap up that, so basically we try to show that, or convince you that sea level fall induces enhanced outgassing via hotspots at mid-ocean ridges. That enables so far hitherto negative, unrecognized negative feedback between glaciation and atmospheric CO2. And so in that sense, we argue that enhanced outgassing at that time of pronounced sea level drop basically helped to stabilize atmospheric CO2 and thereby counteract global cooling. And of course, this just highlights the interaction of traditional global climate components and geosphere interactions. And there's an argumentation from our side that probably the system is more complex and that these sort of interactions potentially have to be taken into account to have a more thorough understanding of the global carbon cycle dynamics on these timescales associated with these processes. So that's it. Thanks.
I wonder if you've thought at all about the flux of alkalinity that you might also see from enhanced weathering of the magma that you produce. So magma produces the acids, right? And you've taken account of the CO2, but it also produces bases. And so there may be a counteracting influence of enhanced alkalinity flux.
Yes, I mean, there are many huge uncertainties, and the biggest uncertainties are probably the way, I mean, what we model here is baseline fluxes, but of course, the transport time scales and the way, for instance, how at mid-ocean ridges the fluids interact with the surrounding materials, so by porosity, and how that really relates to affect the, let's say, geochemical composition along the ridges and also within the water column is really is outside the scope of the study. And but of course, I mean, there are certainly interesting questions that should be addressed in future studies.
Thanks everyone for being here. Today I'm going to talk about really interesting carbon cycle variability that we're starting to be able to observe with the new C13 record from the MIS 5.4 transition, the last glaciation. I'd like to say a big thank you to my co-authors, because through really valuable insights, also through data collaboration, they've made this a much more fun experience and also a much better project. So just taking a step back and looking at the large-scale global climate that characterizes the 5.4 transition, here I'm plotting Antarctic temperature, also benthic O18, and a CO2 composite from the ice cores. And what you can see is I tend to think of the MIS 5.4 or stage 4 really as sort of a mini LGM. And so global temperatures get cool here, glaciers are growing, sea level is falling, and what we're really interested in for this project is this really large, about 40 ppm drop in CO2 that occurs within about 3,000 years. So this implies really major carbon cycle adjustments occurring at that time. And the purpose of this project is to try to put some constraints on what those processes are using the stable isotopes of CO2. So I'm just zooming in more detail in the region that I shaded in the first figure, and now I'm plotting Greenland temperature as well as Antarctic temperature. Here's the benthic O18, the CO2. I have 2 sea level records here, as well as dust from Antarctic ice cores. So generally just painting the picture at higher resolution that sea level's falling, conditions are getting cooler, drier, dustier, and you can really see some structure to the CO2 drop here. So the way that I'm going to tackle this question is we use a really special ice coring site called Taylor Glacier. Basically what happens at Taylor Glacier is that ice accumulates at Taylor Dome, and it flows down Taylor Valley. So this is the glacier here. And what happens actually, because of a combination of folding and sublimation, is that the old stratigraphy gets exposed at the surface of the glacier. So what this means is that we have relatively easy access to large volume samples of ice because the old ice is essentially brought to us by the glaciology. So what we've done is collected a shallow 20-meter ice core, really large diameter ice core, and we collected it from a site where the surface ice is around 55,000 years old. And so what I'd like to do in the next slide is hopefully convince you that this 20-meter ice core contains the 5.4 transition. So what I'm showing you here is how I developed the gas age model. I'm plotting delta O18 of atmospheric oxygen in the ice core, also CO2 and methane. So what I'm doing here is comparing to previously dated ice core records, and I'm hand-picking tie points, mostly from the methane variability, to match the age model. So I get about 11 tie points from the methane, and I get a couple from the delta O18 also. And the CO2, interestingly, is independent of this tie point picking scheme. So when you map the CO2 onto the age model, you can sort of get an independent check of how good it is. And what you see is that we definitely have this large CO2 drop. We have the low CO2 values to the stage 4, and then we have the end of stage 4 and the beginning of AIM 17, the CO2 rise out of stage 4. So hopefully having convinced you that we have a good constraint on the ages, I'm just going to show you some results from the C13 study. So I'm plotting some of the records that I've already showed, Greenland temperature, Antarctic temperature, methane. I'm also showing N2O here. This is the green. I'm showing this is really peripheral to this study, and I'm not really going to talk about N2O anymore, but I did want to show it because it's sort of a indirect byproduct of our mass spectrometry. And it's a really high resolution, nice N2O record. And I think that there are some people like Jochen in the audience that might want to talk about N2O afterwards. So I did want to show that this exists. But what I really want to talk about for the rest of the talk is the CO2 and the C13 results. So the dark red symbols here are our CO2 record, and I'm comparing them to records from EDML and Talos Dome. Those are the light red and light blue and blue dots. And then here is the main new result. The C13 record is the pink diamonds are from Taylor Glacier, and I'm showing the 1 and 2 sigma standard deviation envelope as well. And then what I'm plotting below is the pre-existing C13 data. Those come from a combination of the EDML, Talos Dome, and EDC ice cores. So what's apparent in the record? I think it's clear that there are really, really large changes happening in C13 while CO2 is essentially going down throughout the 5-4 transition. So we have about a 0.4 per mil departure, or excuse me, excursion here. And then this is about 0.75 per mil. C13 gets really, really enriched in stage 4, where CO2 is low. And then the biggest feature of the record starts here, and there's about a 1 per mil lightening of C13 to the end of stage 4. And so I think what this does is it paints a really complex trajectory for this CO2 drawdown in terms of the processes that are occurring. And the last thing I'll say is that there are known offsets between the data from the European cores and our C13 record. This has been a topic of active conversation between the two groups, and unfortunately we just don't have a smoking gun yet to explain the differences. What is really encouraging is that the really big 1 per mil drop occurs in both data sets, so at least on a coarse scale, we're seeing the big changes. So I want to say just a few words about how then do we think about how to interpret these data. What I'm showing here is called a Keeling plot, and you can think of these vectors sort of as mixing lines, though they're not really mixing lines. What they are is carbon cycle perturbations to a box model, and this is from Thomas Bosca's work for the deglaciation. And what you're seeing is that for a given change in CO2 due to a certain carbon cycle process, you're also seeing the change in C13. And this is for the deglaciation, so that's why model time and why all the arrows are going toward increasing CO2. But for the purpose of this, I think you can actually, at least in terms of thinking the direction of change, let's just flip the arrows around to think about the cooling. So just some examples. If you were to cool sea surface temperatures over here, so moving opposite the way that arrow is showing, you would sequester CO2 as the oceans became more soluble, and you would expect decreasing C13 in the atmosphere. Another process that's often invoked for explaining glacial interglacial CO2 changes is changing the efficiency of the ocean biological pump. If you were to increase the efficiency of the ocean biological pump, you would draw down CO2, and you would expect to enrich the atmosphere. So at least in terms of the direction of change of these two variables, I'm hoping this gives us some framework for interpreting the record. So what I'd like to do now, I should say actually the bad news about this. The bad news is that you can have nearly infinite combinations of these things happening at the same time to give you the same result in C13 and CO2 space. And so fundamentally this is an unconstrained problem, given that. But having said that, I do think that it's useful because it gives us a framework for thinking about what dominant processes could be happening at different times. So what I'm doing here is I've just shaded 4 sort of main excursions in the record, and the color coding over here where the data are is the same as the color coding over here. So what I'm going to do is just walk you through 4 big changes that I think we can invoke maybe a dominant process occurring. So the very first thing is this red shading, and what I'm highlighting is this little CO2 uptick. That CO2 increase is directly in phase with northern hemisphere warming associated with DO19, and there's a negative C13 excursion here. So I think that this could be increasing respiration rates in the northern hemisphere and pulse of land carbon. The next big change is shaded by the blue. C13 is getting light and CO2 is decreasing. This is consistent with cooling sea surface temperatures. Following that is a really large enrichment in C13. And this is consistent with increases in the efficiency of the biological pump, possibly because of increases in productivity, possibly increasing stratification. And it's notable that the dust in the same ice core and in other Antarctic ice cores gets high at that time. So you might be starting to think about iron fertilization of the oceans. So CO2 is drawn down, CO2 stays low, C13 stays high, and then the next big excursion is the 1 per mil drop when CO2 starts to rise at the end of stage 4. And I think one simple interpretation is that the CO2 that went into the ocean because of this changes and comes out. So the next question I asked is, can we look at what constraints we have from the paleo records to sort of maybe validate some of these large-scale process changes? And I think what's most interesting here, this is a sea surface temperature record from alkanones from the Southern Ocean core, and actually there's a pretty large sea surface temperature change that occurs where I think that sea surface temperature cooling is consistent with the CO2 and C13. And I know there are air uncertainty, age uncertainties in some of these records, but I'm using the published timescales, and the results are really encouraging in terms of lining them up for now, at least. So the other big change is where CO2 falls and C13 gets very enriched, and I think that there might be increased productivity or some change in the efficiency of the ocean biological pump. In phase with the increase in dust is also an increase in alkanone flux to the Southern Ocean, and this record is interpreted as a paleo productivity proxy. And then lastly, I'm showing this because I want to show you sort of the way I'm thinking about this more quantitatively and the way I want to move it forward. So I've constructed a really simple box model of the carbon cycle, and it has a lot of deficiencies at this point. And so what I want to be clear about is that I'm not modeling reality here, but I'm using this as a teaching tool for myself to learn about the carbon cycle. And what I'm doing is just giving it the individual perturbations that I just described in the previous slides. So I first have a land pulse of carbon, which causes the CO2 increase, C13 decrease. I cool the sea surface temperatures by a couple of degrees, and then I get this excursion. And then I increase productivity, export productivity, and I'm able to get enriched C13 values. Again, I don't think this is reality, but what I'm excited about is that you can get a complex trajectory in C13 from relatively simple individual changes to the carbon cycle. And I think this does represent a way that I can take this forward with more development. So what I'm going to do is just finish with a very conservative and general summary. But I think what's happening is that we're starting to look at the carbon cycle changes in these very much more detail than we have before. And I think we're actually picking out sort of the timing of these distinct changes. So I'll stop there and take questions.
It's really interesting that in your box model, the CO2 keeps going down lower and lower, but the atmospheric record stays high. Any thoughts about that mismatch?
You're talking about this here?
Yeah.
Yeah, so that's exactly the kind of mismatch that I don't want to interpret yet in this box model. But what I would say is that I want to be confident enough in my model that I can start to interpret those kinds of mismatches. So to run experiments where, let's say, you do get the C13 change that you want, but the CO2 is off, I think that in maybe a different context, that would imply that you're missing processes, possibly volcanic CO2.
After this very good warm-up about a lot of CO2, I hope I'm confident that you're now ready to face methane. I'm going to talk about the shift in the interglacial methane budget from 2 unstable isotope records. And first I'm going to start with a little introduction about methane. Here you see 5 glacial cycles in methane. Time is running from the right to the left. And well, kind of the reason for our study is we want to find out whether the Holocene behaves as a normal interglacial or whether it's somehow different. And therefore, we measured ice core samples on the following interglacial, so the Holocene, the marine isotope stage 5, and Miss 11. And also on the glacial periods, the LGM, the Miss 6, and the Miss 12. And we heard a lot about isotopes, so I don't have to go into detail with how the isotopes works. Pretty thing is that they kind of there are two isotopes, stable isotopes of methane: the delta deuterium, the hydrogen isotope, and delta 13C. And all the different sources producing methane are somewhere allocated within this plot. And here in green, it's more the microbial sources. In brownish color, it's geological sources, and the red one is biomass burning. They all add up together to this source mix, and the fractionation of the sinks lead to this very strong fractionation, and we end up with the tropospheric values, and that's what we were able to measure in the atmosphere and also in the ice cores. And in Bern we have the devices to measure both stable isotopes of methane, and we've done that on those periods I showed. So here again on the uppermost panel it's methane. Please note that the axes are now broken, so that we can really focus onto our targets. And on the lowest panel there's the CO2 concentration, and the two panels in the middle are showing the stable isotopes of methane. In the blue and purple here it's delta deuterium, and delta 13C is here shown in orange. I also have to say that the axes for the isotopes are inverted, so heavier numbers are further down, whereas the light numbers are up. It's the same for both axes. And yeah, we're really happy with this very nice data, and we were able to extend the time coverage from by a huge amount, and also the quality of the data is very nice. So we're quite happy with that. And there are a few quite nice features. For example, these deglaciations in delta deuterium are quite remarkable. They seem somehow to work different. So here it's quite a gradual deglaciation, whereas for the Miss 6 to 5, it's very fast jump. And for the Holocene transition, again, it's more something in between. Another feature which we were already knew about it, but again, it's nice to see it, is that decoupling from delta 13C from the methane concentration record. So what I want to say is that the delta 13C record is much better correlated to CO2 than to the methane, and that's quite. We already know that from the Muller study, but it's still visible here, and it's still quite extraordinary, I think. But probably the most prominent feature of our new data set is the difference of the levels, of absolute levels. So if we see here in both isotopes, the level of the Miss 11 and Miss 5 just doesn't fit with the Holocene. So there is a huge shift towards heavier numbers in both isotopes. And also for the glacials, the same is true. So the glacial values also are heavier in the LGM than in the other glacials. And at the same time, we don't see anything like that in the concentration record. So the concentration, they don't look suspicious, and therefore we wanted to have a good explanation. And I go back to our isotope chart here, because there are two kinds of explanations. The first one is if we change the source signature of an important methane source, for example, tropical wetlands or something. So if we change the signature, then the whole source mix will move. But there's just no evidence from other proxy data that such a change in the precursor material should have happened. And therefore, we don't really believe in that. And the other thing is that we take a source or a process which is far away from the source mix, so has a strong leverage on the isotopic signature to explain such a change. And first we go with the geologic emissions, but there it's the same. They're thought to be kind of controlled by, for example, sea level or ice sheet extent, and there's no real reason why that should have been that much different from the previous interglacials to the Holocene. So that's ruled out as well. And we end up with biomass burning, which is another very heavy source. And that's the point when I go to more the hypothetical pathway, because I want to explain you why there should be more biomass burning due to megafauna extinction. Okay, megafauna is thought to have a huge impact on plant coverage. First of all, by just consuming fuel for biomass burning or for fires, and secondly, also to lead to a structure change. So here's the situation shown with megafauna or large herbivores, and here they're just small animals eating plants. And you see that here's less fuel for fires, but also the structure is different, so fires can't distribute as well. And there are studies, for example, here this is a lake sediments data from Australia, showing that megafauna declined somewhere 40 years ago. The brown curve here is Sporonmiella, which is a good proxy for large herbivores, and somewhere there they just decline. And at the same time, there's a huge change in the biome. So plants changed, and also the microcharcoal indicates that the fire frequency or increases at the same time. Obviously, that's just one local study, but there are more of them in North America and other places. But it's quite hard to estimate the impact of something like this on the global methane, and therefore we use not the bottom-up approach, but like a top-down thing with a very simple box model. We have 4 boxes, 2 tropospheric boxes, 2 stratospheric boxes for north and south. We have a prescribed air mass exchange, and we have sinks, and we have the sources. And we run the model in the Monte Carlo framework, which means that we just roll the dice for the sources and check, let the model run into equilibrium, and then check whether here's Antarctica, whether this fits with our measured data, what remains in the troposphere. And we do that many times, and if this fits, we store the data of our sources and do this as long as till we get 10,000 valid scenarios of emissions for each time slice. And that's mainly the result, or here we see the scatter plot, biomass burning versus geological emissions of methane. And for each time period, there's this curve indicating the whole, the other way around. All 10,000 found solutions lay within this curve, for example, for the Holocene. And this is done for all the periods. And now you see, first of all, we see a very nice negative correlation in all those curves, which is kind of clear because the heavy sources, they counterbalance each other, and if there's to fulfill the stable isotope constraint. And secondly, we also see the shift. So the Holocene and the LGM are both moved to the upper right, which means which comes also from the isotope constraint. And this is like this. Now we have a chance to kind of quantify a little bit how much biomass burning would have to be needed. So if you look, for example, at the upper limit of those curves and set the geological emissions of methane at a reasonable value, which is in this case 30 teragram per year, then we need an increase from 18 to 33 teragram of methane per year, which is quite a large increase. And with that, I'm trying to summarize. So here again, you see our new data. I hope you're convinced that this is very cool data with many interesting features. the Holocene is somehow really heavier than all the other interglacials, and there might be explained by wildfire change in the wildfire regime, maybe due to megafauna extinction. Thank you.
I'm just curious. I'm pretty interested in the CO2 C13 of methane correlation, and could that be indicative of a southern source for the methane?
Of a southern source.
Of a southern source.
We think more that it is about I mean, CO2 is going along climate, and the plant C4, C3 ratio of the plants are moving along the CO2 because there's just other plants in favor of high CO2 levels, and that this has an impact on the C13 level of methane. That's the way we think. I don't know what you mean with the southern source.
Oh, just thinking about CO2 changes being correlated with southern temperature changes. Possibly turning on or turning off a southern source.
Yeah, probably. I don't know. Yeah.
About the Holocene, you try to explain the different isotopic composition only with the sources. Does it make sense to not think about? I mean, I don't know. The sinks didn't they change as well? Or?
Yeah, sinks are always another loophole as well. Yeah, that's true. But there are studies around which show that these changes shouldn't be that large. So, yeah, but always things are always possible. Yeah, that's true.
Okay, thank you.
Thanks very much. Thank you all for sticking around for the last talk. I know you're all excited to go out for the photo, so hopefully this will be nice and fast. And after Jonas's lovely distraction with methane, I'll be bringing us back to a slightly more important greenhouse gas. Take that. So I'll be talking about CO2 again. And of course, we've already seen this, this plot. So time in all of my plots will be going from right to left, showing CO2 and delta deuterium. And one of the plots that we haven't seen yet, I think, well, not the whole plot anyway, is the dust plot. So this is another EDC dust plot over the last 800,000 years, showing that with the drawdown of CO2, the low temperatures, we always see this rise in the dust flux to the Southern Ocean. And so that has been the cause of the hypothesis, the iron hypothesis that was put forth first in 1990, which basically draws on the importance of the soft tissue pump in the Southern Ocean as a drawdown of atmospheric CO2. So the goal of this study is to zoom in on the last glacial cycle and try to get a handle on what the soft tissue pump was doing based on records that, I'm not going to be showing any new data, but lots of old data that I hope I can convince you are worth looking at in a little more detail. The basic idea, so I'm following up on the last few talks where I'm also splitting up the ocean into 4 boxes. Very convenient. And so I've got low latitudes on the right, high latitudes on the left, surface ocean or above 2,000 meters, and then deep ocean. So I'm going to be talking about 13C here, which we also just heard about, and what this looks like in the ocean. So this is a very basic framework. Of course, there are many processes that are affecting this, but the basic idea is we have gas exchange that is setting the atmospheric delta 13C. Gas exchange is happening everywhere to different extents. We have photosynthesis in the surface ocean then, that with rising photosynthesis or increased soft tissue pump efficiency, we get a rise in the delta 13C at the surface because the photosynthesizers are taking up light carbon. At high latitudes, we have deep water formation, which is bringing down whatever surface delta 13C signal we have down to the depths, and this is filling the oceans. So at depth, we would expect relatively uniform signal. And then if we look at, so the idea here that I'm going to try to convince you is maybe not a bad idea, is looking at the difference between the delta 13C in the surface ocean and at low latitudes, and the delta 13C in the deep ocean at low latitudes to get a handle on the soft tissue pump. Of course, there are many other processes that are affecting this, so this is not yet quantitative, but I hope to convince you that it could be a qualitative measure and also shows very interesting results already. So to do this, I've been working with Olivier Katpernis and Sam Jacquard, as well as Eric Galbraith. Olivier has put together a wonderful database of more than 9,000 records that are gathered mostly from Pangaea and NOAA, as well as some other individual records. And this is a database not only of delta 13C, but it also includes delta 18O of carbonates as well, opal, carbonates, total organic carbon, sea surface temperature, and other proxies. There's a global distribution. I'll show a couple of plots later of where our data here are coming from. And it includes both planktic and benthic foraminifera. So we have already heard in one of the questions, how well can we interpret an individual planktic record? And I hope to convince you that maybe the individual planktic records have issues, especially with vital effects, and they are difficult to interpret. But if we look at a global distribution, it looks like it does make sense to actually use these data just as well as using the benthic data. So the whole point of this is that it's useful for a global analysis. We're not looking at regional effects here. And this database has been detailed in more detail by Olivier in his recent Nature Communications paper, which is also very interesting. So where our cores are here. We've got the planktic the benthic records. And the planktic records, I'm not going to go into detail about the colors right now. These are records that are covering the last 150,000 years. So you can see there is some spatial bias. We have a lot in the Atlantic and not as many in the Pacific, very few in the Southern Ocean. And if we look at the benthic records with depth, we can also see that there is a bit of a spread there. So we do have a lot at depths in the southern hemisphere, and some more shallower cores at the higher latitudes in the northern hemisphere. I mentioned we're going to split up the ocean into 4 boxes. So these 4 boxes look like this in the benthic records. We've got the high latitudes, the shallow high latitudes, which you'll notice only have 1 core. So I'm not going to be plotting those in the subsequent plots. But in the other records, so we have the high latitude deep boxes, which have a few cores. These are all in the southern hemisphere. And then the low latitudes, we have a lot more. So both the shallow and the deep. In the planktics, so I'm actually adding 2 more boxes, which are planktics at high latitudes and low latitudes. We looked at planktics with depth, and we didn't see a dependence, which is comforting, because if something is living at the surface, it shouldn't really care about how much water is beneath it. So this is what that looks like. We've got these 6 boxes, 7 including the atmosphere. So I'll be referring to these A and B as the planktics, C, D as the shallow benthics at high lats and low lats, and then E and F in the subsequent plots. This is what the 18O data look like. So we're taking a very rough, just a mean of all of the records. So first we interpolate to 1 kiloyear time steps, and then we take, for example, in box D, that's the dark red here, we take the mean of all of the records there. So this is not yet weighted. That will be in future work. But this is what the data look like. And the comforting thing on 18O, the only reason I'm showing this right now is because we want to make sure that the age scales of all the records are aligned. And I think, at least I'm convinced, I hope you are too, that it's a reasonable thing to do, to say, okay, yes, these records align. So looking at the delta 13C, this is maybe even more exciting. We see, I've shown the atmosphere is the spline, not yet including the new data from Andy Menking, but the spline of the last glacial cycle. The blue lines are showing the high latitude data, and then the red lines are showing the low latitude data, with the lighter colors at shallow depths, and then the darker colors at deeper depths. And I think the most exciting thing here, so of course the one thing I should say is that the atmospheric record is on a different scale, but the difference, so the magnitude here is the same as the magnitude with the foraminifera. And we can see, I think, just looking at this, that we have amazing alignment. So I've colored this now in basically just making a broad generalization, but I think hopefully it's not too far off. These, the four boxes here that are colored in blue, so the high latitude ocean as well as the low latitude deep ocean, all show a very similar pattern. I have, of course, not plotted box C because we only have one box, so maybe this should still be gray. But in any case, we do have in A, E, and F, so kind of following our theoretical framework that I put forward at the very beginning, we actually do see a very similar pattern. Whereas the atmosphere and the low latitude planktics, as well as the shallow benthics, all kind of agree on this red line that I'm calling pattern number 2. So this is very interesting. One other note is that these data are all centered. So all of the records are centered to 0 at the LGM, which is why they all fall here. In reality, the planktic records are actually higher in magnitude. So the red line should actually lie over the blue line. This was just to simplify the analysis that I've plotted them this way. So this is what that box looks like in a little bit zoomed in. And the idea now is that if we take the difference between the red line and the underlying blue line, so that would be, as I mentioned, taking the difference in the box D and F, for example, or we can also look at B and F, then we might be able to get a handle on what is happening in the soft tissue pump over the last glacial cycle. Another thing to note is that, so as I mentioned, planktics, individual planktics have been known to have issues, but I think these records have shown that the many records that we have in box B, when we average them, all show a pretty reasonable agreement with box D. So that's very exciting. What happens if we look at these differences? So these are the two that I just mentioned. So cyan is the planktics, using the planktics, and then green is just using benthics, so shallow benthics minus deep benthics. This is what it looks like. And there's a lot going on here. I do want to be cautious about interpreting things like this because this is only one point and could represent only one outlier in one data set, since the number of data sets varies along the time scale. But so I'm not going to go into too much detail, but a couple of interesting things are in the marine isotope stage 5, in the substages, we do see these peaks. So this is increasing soft tissue pump, so an increasing in this direction. One major thing that I do want to point to, though, which I think, getting back to what Andy said, of thinking of marine isotope stage 4 as a mini interglacial, this is what I have also thought in the past, but I think there is increasing evidence that maybe there was a difference between marine isotope stage 4 and the last glacial maximum. It wasn't that just everything was, it was almost as cold but not quite, and the ice sheets were almost as far but not quite. I think this is actually showing that the peak here, and of course the error bars, because these are based on many records, are large, so this is not, it's not too significant, but it's not statistically significant, but it is, we do see it in the record, that the peak here is actually, in the difference, is actually larger than what we see at either of the marine isotope stage 6, so the penultimate glacial maximum and the last glacial maximum, marine isotope stage 2, which might actually indicate that the soft tissue pump was possibly more efficient at marine isotope stage 4 compared to stage 2. Just to quickly wrap up, this is my last slide of data, but this is in agreement with nitrogen isotopes. So this is showing nitrogen isotopes from the NICOP database. So a different database, also using globally averaged, globally measured nitrogen isotopes. On the top, I'm showing 15N itself from the global collection. The second plot is just looking at the Southern Ocean, and the last plot is the CO2. So the top plot is actually showing a slightly higher delta 15N at the LGM, so the axes are just reversed, compared to marine isotope stage 4. The error bars are also large, so maybe the biological pump was slightly weaker according to the 15N data as well. The Southern Ocean data are indicating it looks like more complete nitrate consumption during marine isotope stage 4, which could actually mean that the lower CO2 is a sign of stronger limitation of nitrogen fixers. So again, as I said, we're still in progress here, but just to wrap up this talk very quickly, I hope that I was able to convince you that the pelagic records, maybe if we average them over large geographical areas, they do show us what we expect, and maybe we can kind of average over the problems in individual records. We saw these two main signals in red, so in the atmosphere and the low latitudes, compared to blue in the deep ocean and the high latitudes, which maybe is an indicator that we could look at this delta 13C as a proxy, a qualitative proxy anyway at this point, for the soft tissue pump strength, which in this case would then maybe indicate that we did see more, a stronger biological soft tissue pump during marine isotope stage 4 compared to the last glacial maximum. As I mentioned, we are still working on this, so we are hoping to include more data sets which will flesh out especially the high latitudes, especially this box without much data. And then we're also looking to work on a whole ocean 13C budget over the last glacial cycle in order to look at also changes in the terrestrial biosphere in addition to the atmosphere-ocean system. So, thank you very much.
If you assume a constant biological pump and you increase the residence time of deep water, I think the delta C13 will be increased. Have you thought about this?
Not in great detail, is the short answer. I think, yeah, no, I would be happy to talk to you about this later. There are many things that are affecting the 13C signal, as I mentioned. So it is also possible that we're seeing imprints from other things apart from, and I think very likely that we're seeing effects of other processes. I mean, also, yes, changes in circulation is a great candidate for that. But yeah, future work. Thank you.
So I was going to ask something very similar, but maybe I'll throw you a bone there and say, when you were saying kind of net efficiency of the soft tissue pump, I was thinking that perhaps you're really thinking of some convolved signal of both the circulation component and the productivity component.
Yes, yeah, so that's very true. So this signal is actually, for those of you who may have seen my talk at the Young Scientist meeting, I was talking there about I was actually kind of downplaying the importance of the soft tissue pump and talking about the importance of disequilibrium carbon in the surface ocean, which is basically the residual that you have based on the fact that the ocean and the atmosphere are not in equilibrium at the surface, because air-sea gas exchange is not infinitely fast. So this signal is actually, what we're seeing is a combination of both that disequilibrium signal and the soft tissue pump. So that is very true. And the disequilibrium carbon itself is a function of circulation and air-sea exchange. So yes, thank you for the, thanks for the bone. I'll take it.